So thus far, we've basically focused on the automating production side of things, where you're thinking about final output that's produced by tasks or capital and labor, and we're saying, can the labor be replaced by capital? The other term that we've basically been assuming is growing exogenously is the level of technical, the level of technology, the A term. And another case for an AI growth explosion, or what AI could do to growth, is thinking about how AI could automate the production of that level of technology, automate research. I'm going to start off by just presenting a few slides on evidence for thinking about that, and then Phil will get more into the theory side of things. But as I just said, most studies of the economic impacts of AI think about the production side. Perhaps that's because it's easier to measure production. R&D and technological progress is a bit fuzzier to measure. Historically, when we think about automation, we mainly think about production. We think about, Ford factories, Excel, whatever, not necessarily the research side. And specifically, low skill work is what has been automated, whereas R&D is high skill. But obviously, LLMs seem like perhaps they're more geared towards these high-skilled R&D areas. Another reason maybe people tend to focus on production is that as a share of GDP, R&D is small. And so you might think that unless AI has a huge impact on R&D, it's not going to affect GDP that much. But you could imagine that if you think long-run growth is mostly driven by technological progress, compounded over a long time, or if a long time is compressed into a short amount of time due to AI progress, this could end up being really important. And then finally, researcher chauvinism is another potential reason maybe we don't want to think about ourselves getting automated.
More concretely, I'm just reminded of that survey from Classic Grace where the AI said that AI research would be one of the last things automated, and drug would be automated soon, but other kinds of research would also be automated soon. Just like in general, maybe people think that their own work is more complex than everyone else.
Yeah. Another reason perhaps that people focus on automation in other sectors is historically R&D is much more labor intensive than the economy as a whole. So the economy as a whole has a capital share, the private non-farm business sector, of 30 to 40%, somewhere over here. But R&D sectors, the capital share currently is much lower, which is a reason that perhaps we don't think of R&D as something that's automatable, but this could change. Some reasons why AI may come for R&D first, first and foremost, AI's output from current LLMs is information. It's ideas. It's not like a physical technology that just substitutes in one production line. And that makes it natural to think about it as impacting to the level of technology. In the Alondo and all exposure metric, coincidentally, the top two most LLM exposed job groups are scientists and researchers and technologists. So this seems very connected to R&D technological production. Philip Trammell, finds that R&D occupations are slightly more exposed than average in the Alondo and all measure as well. And then there's this paper from Babina and al. Showing that AI mainly contributes to firm-level growth via product innovation. And you might think that innovation is suggestive of it being R&D rather than tasks that are being impacted. Some context on that Babina and al. Paper is that's actually using just 2010 to 2018 data and looking at kind of the previous iteration of what we might think of as AI, so computer vision, machine learning, natural language processing. But they they quite convincingly show that if you look at, that they have these cool measures of how much AI workforce different firms are hiring, and then they show that firms that more intensively hired workers who are in these AI positions 2010 to 2018 ended up producing more patents, having more product innovation, but not having just cost savings on the production side. So it did seem like at least that wave of AI contributed more to the R&D side than the production automation side. Did you have a question, Sandra? Yeah. So I don't think the longitudinal, like the ONET classification distinguishes between, dev economists and econometricians or anything like that. I do think economist is different from scientist and researcher.
On experiment. But I don't know the name exactly, but it does split being an economist into different tasks, of which at least one is basically run experiments and another is develop models.
And in the afternoon lecture, we're actually going to show you a figure where we look at like 11 different sorts of researchers and their tasks and how exposed they are to like purely cognitive work versus involving physical work. So there'll be a little bit more about that. And AI's most impressive achievements to date, obviously, I think most people would agree, have been scientific, most notably the development of AlphaFold, which led to the chemistry Nobel for Hassabis. And you can think of, I think is probably considered to be the most notable AI achievement to date. And even if we think this scenario is less likely, it may be more important. You can imagine that, again, if you think that long-run growth is mostly driven by technological progress, automating R&D might be more important than automating production. And you can clearly think about how automating R&D leads to automating production, while the other mechanism is less clear. But presumably, if the AIs get good enough at R&D, we're going to be able to figure out how to automate production, because they're going to be able to do the things that we have already done historically to automate production much better. Yeah.
When you say automation, do you mean full automation? Because I think of, yes, okay, AI is perfect in running code, but also doing math, but then there's also this discussion on research taste, etc. I guess somebody sets AlphaFold that, okay, let's work on the protein.
So both full automation and partial automation are going to matter for growth. Obviously, the extreme growth scenarios are going to load more on full automation, but we're going to be thinking about the path to full automation as the whole thing.
Task automation for researchers?
We're not going to be looking at R&D as itself a task-based model, but we are at some point. Sorry, but you could also just think about it as R&D production being some function of capital and labor, and maybe at first they're complements, but maybe AI makes it so they're substitutes. Just to get into evidence on research automation pre-LLMs, like there's big literature on how neural nets and deep learning have impacted science, drug discovery, biomolecular interactions, functional genomics, nanotheranostics, electrocatalyst design. Mostly this work's been done by scientists and does not feature the productivity measures that economists care most about. I think maybe one important exception to this is this Merchant et al. Science paper. I'm not going to pretend to understand that paper deeply, but it shows that graph networks trained with deep learning can increase the efficiency of materials discovery by an order of magnitude. And interestingly, the neural networks being used there follow the same sorts of scaling laws that LLMs do. Prediction accuracy follows a power law with respect to data, and that suggests there's some portability in the way these other types of non-LLM AIs could impact research, and LLMs could. It is important to note that all these sorts of papers are focusing on the search space in science, but then there's also the experiment stage, which you might think is more labor intensive and harder to automate. I also should say that the most exciting evidence about pre-LLM research automation was probably that Aidan Toner Rogers paper, which is now not something we're going to be talking about. If you aren't familiar with that, you should ask someone else in the class about it. Yeah.
This is also material sciences, but this one exists, right?
This is real data. This is published in Science. Yes. And then we can also think about how LLMs are impacting research already. I think one particularly interesting example is AlphaEvolve. This is something Google has released. It's an ensemble coding model built on top of multiple Gemini-based models that call them all in some sophisticated scaffolded way. And they have this paper or report where they release that using Alpha Evolve has already at Google improved data center scheduling to continuously recover 0.7 of Google's compute. I think you can think about that as just like saving 0.7% of compute usage across any given fixed time horizon. Alpha Evolve also helped optimize arithmetic circuits for matrix multiplication for Google's TPUs, reduced Gemini's training time by 1%, also via matrix multiplication optimization, and in 10 of 50 open problems in mathematics and algorithms, Alpha Evolve improved the previously best known solutions. And you can obviously think about if these systems are already speeding up TPUs and conserving on compute usage, this process could accelerate where you get more and more speed up, more and more compute efficiency, and this accelerates the development of AI. Oh.
Can go back to a workout question. Should I think about all these uses as full automation or kind of like a more augmenting use where the people on Google are like working with Alpha Evolve and like stating a problem, trying to fix it, and going back and checking it? Do you know the nature of this?
I think, I mean, we're going to get more into some evidence on this, and Parker and Cheryl have some work on this. I think right now it seems reasonable to think about it more as augmentation, but you could somewhat make the case either direction. Someone else can override if they disagree with that. I think this seems to be more like augmentation. Yeah.
One of the lessons I was hoping to communicate with the simple IGN Jones task-based model is that it depends on the level of analysis you're looking at. At the task level, it's generally automation. And at the like research workflow level, it's probably augmentation. That means frees people up to do their things that have not their first product.
I think with Alpha Evolve was pretty much a basically pointed in the right direction, and that really did a lot of it's just confidential search stuff guided by LLMs basically.
I just add that at the occupation level, at least the Otter Thompson framework, it depends on which tasks you're automating. If you're automating the easy thing, then you're sort of augmenting expertise. Whereas if you automate the hard thing, then you're sort of
and you know, these are studies that we've already mentioned before about just the speed up to software engineers, but I do think speed ups to software engineers are perhaps particularly relevant for thinking about automating R&D if we presume that a lot of what AI R&D consists of is somewhat analogous to software engineering or involves some software engineering. Not going to talk about these studies again in detail, but I think it's something to think about. Anecdotally, we hear these reports from the labs that the existing models are already an important part of their production process. There's this quote from Anthropic's chief product officer, Mike Krieger, where he said that something like over 70% of Anthropic's pull requests are now Claude-generated code. That would obviously be AI enhancing their R&D process. And I threw this in last night when I saw on Twitter that there is some open problem in convex optimization that supposedly GPT-5 made progress on. There was some back and forth about it, so I don't know how seriously we should take it, but I do think it's an example of how LLMs might accelerate research. Yeah. Yeah. Yeah, yeah, yeah. Open to the LLM, perhaps. I think maybe the most interesting study to date on how LLMs could accelerate AI research specifically is this Meter paper on automated kernel engineering. And again, I'll have to defer to the computer science experts who understands kernels better than me. But my understanding is compute kernels are programs that are used for model training and inference. And Meter studied 239 kernel writing tasks where the kernels were being used for inference. So the kernel is some sort of code that optimizes the way an existing large language model performs inference. Meter took 4.0, 3.5 Sonnet, 0.1, 0.3 Mini High, put some scaffolding on top of them to create this kernel agent, one for each of the models, like a kernel agent 4.0, a kernel agent 0.1, et cetera. And then would run the kernel agent so that the AI spit out lots of different possible solutions to the kernel writing task and then picked the best of K of those solutions, or the best of all their solutions, and was then able to get that relative to the existing solutions for how these kernels run, the best of all models per problem sped up code runtime by 2x, which would seem to directly be something that contributes to AI progress. Some caveats on that study are that the implementations are a naive PyTorch rather than highly optimized CUDA. It seems like these are more like small scale kernels that aren't reflective of the sorts of complex kernels that are actually happening at the leading labs. All of the problems were on a single GPU, while what the labs are doing is complex kernels that involve communication across lots of GPUs. And the benchmark here is like what was already available on the internet on kernel bench, rather than comparing the AI with another human who was given the same task of speeding up this kernel. So I think it makes it a bit hard to interpret. They do find that if you take into account the costs of developing kernel agent and running the model inference costs, but then were to use this new sped up kernel to perform inference going forward, optimized inference kernels would recover the costs of this optimization after 27 hours of usage, which is, in their accounting, much less than the amount of input that we pay humans for to speed up kernels in the current paradigm. And interestingly, they actually find that within their kernel tasks, they order them by complexity, and the performance improved more on more complex kernel tasks. So I think that's some evidence that it's not just the low-hanging fruit that the AIs are helping speed up. And we've talked, I already talked about it once, Eric talked about it, but I think this is a place to talk in a bit more detail about the Meter developer productivity study. As mentioned, when developers use AI tools, they take 19% longer than without AI in this RCT. Just to give you more details about it, the setting is 16 experienced developers working on open problems in large open source repositories they had already worked on for years. They were randomly assigned to use AI. Typically, they used Cursor Pro, primarily with Claude 3.5 or 3.7 in March and February and March of this year. There's been some talk that the reason they found slowdown is because these developers weren't experienced with using Claude code. I think that's a bit of a misinterpretation. All of the developers had, self-reported that they used LLMs a bunch over the years. About 44% of them had used Cursor before, and the negative results hold for that subset. So even if all of the developers hadn't used Cursor a ton, they were very familiar using AI tools to code. The tasks were on average 2 hours, and Meter did a very good job for I think over 60% of the tasks, screen recording to track actually how AI was being used, and these numbers are legitimate. Total 110 tasks done without AI, 136 with AI. The average result that 19% were slowed down does mask some heterogeneity. 4 of the 16 developers saw an average speed increase, but the average result is that they were slower. And that's despite the fact that the developers, even after doing the task, believe the AI had sped them up 20%. One explanation is that in large code bases with experienced developers, existing AI tends to hinder more than help. I think what I take away from this is that when people at Anthropic say we're already using Claude to speed up our production, 70% of our pull requests involve Claude, well, potentially that's a similar sort of environment to this one, where it's a very high context environment, and maybe the developers are a bit fooled about how much the AI is helping them in that context. Now I'm going to turn it over to Phil to talk more about the evidence, or the models that go into this.
The theory. So, yeah, thanks. Great, so we're going to kind of go in reverse order from how we thought about automating production. on Monday and Tuesday, mainly Monday, we thought about automating production incrementally, task by task. And yesterday, we talked about what happens if you just take the sort of 1 or 2 line macro model and swap out an L with a K. And here we'll go in reverse order. So let's say you start out with a model in which labor and capital are gross complements in both the production and the R&D sector. Fixing the fraction of our labor that we're allocating to R&D, output's going to be proportional to the population times how productive they are, right? I say it won't equal that because if you've got fraction S of the people doing R&D, you're only getting 1 minus S times AL out of the production. But we're fixing the S, so Y is proportional to AL. And the rate at which we're creating new technology is proportional to that standard Jones formula, right? You've got the ideas getting harder to find at rate beta. Old tech helps with the creation of new tech. That's just like it helps with production. That's the 1. And you've got a potential parallelizability penalty that having 2 researchers working side by side doesn't crank out ideas as quickly as having 1 working 2 years in a row if lambda is less than 1. Because of, the replication argument not holding in the case of R&D, because creating the same idea twice isn't worthwhile. So if you have duplicated work, that should be discounted. Okay, so starting from there, if capital becomes a Cobb-Douglas input to R&D, so we just move up to the threshold from the gross complements case, say it shares alpha, then that's our new R&D function, right? And if it becomes a gross substitute, we can basically ignore the labor and say, technology grows like that. Because same old argument. It's going to be like, K plus L to the lambda. But in time, K is going to be way bigger than L. And L will be negligible. And indeed, we might just reallocate the L back to production because that's going to be the real bottleneck. Yeah. Pedro?
I'm wondering whether you thought about this, so the replication argument doesn't hold here, so maybe then we think A is not to the power of 1, but we think B is not 0.
No, the replication argument is about why lambda might not be 1. Right? So, because on a given technological frontier, we're fixing A, yeah.
But then could it be also made you think that the replication argument doesn't hold for L here, but division of labor is better in science than something else, so then that pushes the lambda to 1 again.
Mm-hmm. Yeah.
Principle.
Yeah. So this actually came up before. I think in practice, when people try to estimate lambda by looking at the responsiveness to the rate at which firms actually get more productive or produce new products or something when there's some change to R&D subsidies maybe, and then they hire more researchers. The estimates are all over the map, but they're generally between 0 and 1. This could be publication bias because it looks weird to get a number that's less than 0 or greater than 1, right? You see this all the time. But so there's that. There's also the modeling point that I think it's just really annoying to have a model in which the exponent's greater than 1, because if you then want to solve for the optimal path of R&D, okay, then you've got to build in frictions. Why do you have to build in frictions to reallocating people between R&D and production? Why do you need the frictions? Well, because let's say lambda is bigger than 1, let's say it's 2, say, right? Then you want to have people working simultaneously in R&D so that they can, benefit from each other's co-working or whatever is going on there, right? And then switch back to production, right? You want to have them switching back really, really fast. So you get a chattering solution, or chattering it's better to chatter ever faster. so that, in each instant, you can have like the whole population doing R&D and switching back. So obviously that's crazy, but then you have to build in friction, so it's just like, forget it. And then finally, I think that some of the intuition that you might have for like specialization helping in R&D is it can be done over time as well. So like if the specialization is literally that like you need a lot of different people operating some big piece of equipment at the same time, then yeah, you can get an exponent greater than 1, right? But if there's like different fields, right? If there's like different topics in economics to explore or whatever, then like, yeah, there can be these fads. And like, every micro paper is about Bayesian persuasion for a couple of years. And then we like move on to something else. It's, you're getting increasing returns from specialization, but it doesn't matter whether it's sort of happening at the same time or over time. See what I'm saying? So,
really amazing, like for feedback, so that everyone has to be in the room at the same time.
But are they so good that like is it better to have twice as many people in the room than to have half as many people but get to like deliver it twice? I feel like that's got to be better. That's actually way better, right? Because people can't speak at the same time. It's better to, well, you can't hear them at the same time. All right. So yeah, the first thing to notice is that we're already kind of building, like the initial function already looks kind of Cobb-Douglas, right? And so there's fixing labor. The Cobb-Douglas case looks just like the gross substitutes case. You just, this will just be a constant. And you can just sort of, okay, so A dot's going to be proportional to k to a power in both cases. And it's just about what that power is. See what I mean? So it's sort of the Cobb-Douglas case and the gross substitutes case are kind of the same model here. Okay. So if we just sort of take our like benchmark parameter estimates for R&D in the Jones model at least, and you imagine what happens if you automate it, even fully automate it, not just Cobb-Douglas, you'll conclude that automating R&D in isolation is insufficient for explosive growth. Why? Well, automating R&D, you swap out the L for a K in the idea production function. K is going to be proportional to output, right? Capital's accumulated past output, which is AL. And that bumps up the exponent on A on the right-hand side, right? Instead of it being 1 minus beta, it becomes 1 plus lambda minus beta. Because now technology is, like more advanced technology facilitates the creation of yet more advanced technology through a new channel than before. This new channel is that when technology is more advanced, workers can create more capital, which itself is being used in R&D. So you get the extra plus 1 on the right, or well, plus lambda because of the parallelizability. And then you divide through by A to get the proportional growth rate of A. Now it's a lambda minus beta on the right-hand side rather than the just minus beta that you would have had if R&D was not automated. Okay, so this capital that we're using in R&D is going to be proportional to output because capital is always in the long run proportional to output unless the savings rate is falling to 0. And look at the top of this slide here. Output is proportional to AL because what A is just how productive people are at making output. Great. Got that? Okay. So automating R&D increases the exponent on A on the right-hand side there. You get an extra lambda. The question is whether that extra lambda is enough to move us into a regime of explosive growth. Something that's just really good to know, and you can see how to derive it in the endnote here if you're not already familiar with it, is that if you've got the growth rate of some variable proportional to that variable itself to a power, well, if the power is 0, then the variable is just going to grow exponentially, right? GA is going to be a constant. Yeah? Okay, because a power anything to the 0 is just 1, that's a constant. If the exponent on the right-hand side is less than 0, if it's negative, then the higher a is, the lower its exponential growth rate. And in particular, it turns out it's going to grow power functionally. Okay, so it's going to be like a is a function of time. It's going to be like linear in time, or it's going to be like time squared or whatever. But it's going to be slower than any exponential rate in the long run. And if the exponent on the right-hand side is greater than 1, then a grows hyperbolically, meaning that there is a literal singularity. There's a vertical asymptote such that if that exponent is greater than 1, and sorry, if the exponent is greater than 0, that is if the exponent on the right-hand side of the a dot is greater than 1, the variable grows faster and faster and faster until you get to infinity in finite time. Vertical asymptote. And that's obviously way faster than merely double exponential growth. Does that make sense? Because 2% growth one year, then 4% the next, then 8% the next. That gets really fast after a while, but it never gets to like infinity before Christmas. Okay. Recall that our sort of benchmark estimate of lambda over beta that we've been working with, it's often used, is a third. From the Bloom et al. Observation that the research population has grown at like 6% and the output's grown at like 2%. And you've got that lambda over beta GL is a steady state growth rate of A when research is not automated. You all remember that? You take the growth rate of A, set it to 0, find the steady state. So they say, okay, lambda over beta is a third. If that's right, then automating R&D still raises the growth rate. So it doesn't change the regime, but we just move from a world in which, it remains the case that without population growth, growth is merely power functional. The exponential rate slows. That's the whole Jones point. You need population growth to sustain exponential tech growth, right? That's still going to be the case. But if we have population growth, instead of lambda over beta GL, so 1/3 the population growth rate being the tech growth rate, now it's going to be a half. Why? Because now the steady state, we just have a lambda here that we didn't before. Instead of lambda over beta being the steady state tech growth rate, it's going to be lambda over the new exponent on A, or negative of the new exponent on A, which is not beta, but it's beta minus lambda. So lambda over beta minus lambda GL is the new steady state growth rate. And you don't need to identify lambda and beta separately. Isn't that kind of nice? Because that's the whole challenge. If we know that lambda over beta is a third, just divide top and bottom by beta. You get lambda over beta on the top, that's a third, over 1 minus a third. So a third over 2/3 is a half. Okay. No explosion, but a bit of a bump. Now, it could be a huge bump in the short run. So let's say that all it takes is chips. Let's put aside all of the other robotics that you might need to automate R&D and just focus on chips, just to illustrate the point qualitatively that you could get a temporary growth spurt. So on some estimates, the human brain performs something like 10 to the 15th computations per second. What that means is that AI software is capable and efficient as the current stock of just NVIDIA GPUs, which are kind of the most advanced GPUs on the whole, but not all computation out there or anything, would support 4 million virtual researchers. which is actually kind of less than I thought going into this, right? You think of computation as so abundant, but there are a lot of heads out there. That would be equivalent to 40% of the current global researcher population. But if we think that AI research is an especially important thing to keep an eye on, because like speeding that up could speed up the rate at which we automate like other kinds of research, and then from there to automating other kinds of work more generally. You might make the comparison between all the chips and all the like current AI researchers, and it's going to be, you know, many times that. And there's a lot of room for our stock of compute, even of advanced GPUs, to grow. It's doubled more than every year for the past 6 years. So going forward, even if only a small fraction of our computing capacity is used for research purposes, it could easily be the case that total research effort in general greatly expands, and certainly on any particular field, including AI. So basically you'll get this growth, and it'll be sustained until you run into some bottleneck or other. One bottleneck you could run into eventually would be just like a lack of electricity, because you're going to need more. Before you've automated production, you'll need more human hands. So like, you know, build the power lines or the solar panels or whatever. But yeah, that's not going to bite for a really long time. AI chips are consuming, even on very conservative estimates, less than a third of a percent of global electricity. Yeah.
Maybe that doesn't, like on the previous slide,
Yeah.
you were referring to AI software as capable / efficient, and I was wondering, like, because you could find like an AI software that does things that humans are capable of, but it's not as efficient.
Absolutely, yeah.
Efficient. Or you just meant to say it's capable and efficient?
Oh, I meant and, yeah, sorry. So the point here is, yeah, I was saying unless the capital requirement for an automated researcher is very high, right? So what I'm saying is, just as like a thought experiment, let's say we figure out a way to do those same 10 to the 15 computations per second that a human researcher is doing, or human AI researcher, but now it's being done by all these GPUs we've stocked up and are continuing to stock up quickly. Like, how much of an increase to the researcher population would that be? But in practice, presumably, the very first, well, you could imagine this going either way, but at least it's certainly conceivable that the very first software we have that lets us do everything a human researcher does on a chip does it in this really roundabout way. That means that, you know, like we know the brain can do whatever it does with 10 to the 15th computations per second, but these chips, you need like 10 to the 30 computations per second or whatever to get the chips to do what the human's doing, because it's way less efficient. In which case, you're not going to be able to support 4 million virtual researchers. You're going to be able to support 4 or something, right? So yeah, so we won't necessarily get this temporary growth spurt, because it could just be that like we start out really inefficient, and like we gradually get more efficient, but by the time we're efficient, we're kind of running into some other bottleneck on the next slide or whatever, and so there's no point at which it's moving really fast. But it could be, and I just sort of think it's worth remembering that when yeah, sorry, that's whatever. It's worth remembering that when looking at this sort of headline result that makes it look like automating R&D would be really small potatoes. It might be small potatoes asymptotically, but still produce a huge burst of technological progress for a while.
I guess going also against my point, you could think of like AI intelligence being more able to like cross-communicate than humans.
Yep. We'll totally get to that. Yeah. So like in particular, one way you might model that is that the lambda could be higher. It could be closer to 1. It could be even greater than 1 when they're AIs than when they're humans. But we're thinking about the benchmark case here. Yeah. Temporary growth spurt. It'll eventually run into either an electricity bottleneck or just the like compute bottleneck. And I think the compute bottleneck is going to be the one that hits sooner on anything like current margins. So in that case, yeah, we create this way to put GPUs to extremely productive uses by having them sort of simulate human researchers. We shift over a lot of our stock to accelerating R&D, but we went out of chips, and we need more and more people to build chips. And then we shift over more and more people to building chips, and then you run out of people, right? And it's only then that you're really at the population bottleneck where R&D can can't grow faster than half the rate at which the population is growing. And even in an advanced economy like the US, IT is still a pretty small share of GDP. If we come up with ways to like automate R&D and all we need is the chips to do it, we could like transfer many people, like wages in that industry would really skyrocket, and people would shift over to building more chips. And so you could have that growth rate faster than half the population growth rate. Just as historically we've had the population of researchers growing way faster than the population overall, because the composition of work changes. And then finally, as Zach was sort of hinting at, a temporary growth spurt could just become permanent because it allows us to invent methods of automating production, right? So by the time the need for human hands to build more chips constraint starts binding, we might have kind of done so much R&D that we figured out how to build the bots that will automate production for us. But anyway, so that's sort of the benchmark. Any questions on the broad strokes of it? Yeah?
I think we're going to start talking about that.
Okay. So the very first point is the one that you were sort of raising, which is that maybe when thinking about a move to research done by AIs, we should imagine that lambda will be higher. Research will be more parallelizable. Different people have expressed this point, thought through this point in different ways over the years, but basically the idea is pretty intuitive, I think. Currently, the only way we can increase cognitive R&D inputs is to throw more humans into the lab, and all that extra compute is kind of hard to coordinate because you have all this latency between the different brains. You have compute coming in like skull-sized packages and communicating with each other through little bursts of air out the mouth. You might expect that there's kind of a much higher lambda when you can kind of increase the size of each very low latency, like very well integrated computational system. People obviously differ from chimpanzees in many ways, but people argue about this. There's some research that seems to suggest that actually maybe our big kind of intelligence advantage on chimpanzees actually just is the brain size thing. So there's just like extremely increasing returns to having a larger brain. I think that's a minority view, but it's a fun thing to think about. And I mean, we'll talk about this afternoon, but like concretely, the way we've been making such faster progress sort of at building bigger models isn't just by throwing more compute at training mainly, but it's been by figuring out ways to use compute simultaneously in an effective way. So like the invention of the transformer and the discovery that you could run it on GPUs meant that the rate at which like the frontier model was like getting better shot up. So like A dot went up, not because K got really high, but because with the old technology we had, with the small chip, with the CPUs and with smaller chips, as you throw more compute at a training run, the rate at which it moves just rises toward a ceiling, basically. Okay? Because you just can't you can't parallelize the training process. Like you could have like, you could fill the galaxy with computers, but it wouldn't be able to like train GPT-4 in like 1 second. There's like a bunch of computations that have to be done in sequence. So see what I'm saying? So that's like really diminishing returns to throwing lots of compute at the problem, the tech problem of like creating the next model at the same time, right? And these discoveries kind of let us absorb more compute simultaneously, because you could parallelize the training process more. So again, we'll talk about that more later, but it's kind of like an advanced raising lambda. You know, a final thought experiment, I think we'd severely underestimate the scale effect of increasing population, just like in production or research, if we imagine that people had to sort of stay on their own farmsteads and only communicate via the, you know, the Pony Express or something, instead of lowering that latency a lot by agglomerating in labs and cities. So, you know, yeah, a further benefit on that dimension by kind of having, yeah, having integrated researchers that aren't just, you know, separate human heads could be really important. Yeah.
But like communication between many parallel instances of the same model.
Yeah.
Is it the same thing as, you know, there's 40 of me to talk to each other versus like all the people in this room, same number of people? Because I can imagine if we actually are like the same model talking to itself, and we're doing some kind of recombination type thing, there's less novel.
Yep. No, that's totally right. That's a reason why if what we do is just have the same, like many copies of the same model talking to each other, if that's like all we can do, then lambda could be lower in the AI case, right? Because you're not getting like new insights as you scale up the number of people. I think that, yeah, I mean, this gets into all sorts of weeds, you know, so, but if you're just sort of starting from the benchmark where you have people that have their different experiences and so on, that are all bringing something to the table, and we're divorcing that from like what we know about how we're actually training LLMs using using the whole same internet and so on. You could imagine that like the path to automating R&D is to just have a bunch of like, you know, research robots or whatever that go out and have like some sample of experiences that's about as diverse as that like different people have. So I'm a little bit reluctant to give up on the idea that the parallelizability you can get with the human case is a lower bound on what you could get in the machine case in principle, right? But in practice, it could be lower as well. And thanks for raising that. Yeah.
Multi-agent LLMs, the most recent IMO result is.
It's a great point.
Working in parallel. It's not a simple LLM.
What is the example, sir?
The IMO result from OpenAI and from DeepMind.
Yeah. No, that's a great point. It's a great point. I mean, do you know anything about like how much of the gains from a mixture of experts model is from the like fact that the experts are different, and how much of it is just from the fact that they're stochastically producing different answers and you can pick the best one?
So this white name is a single.
But it's like a sparse model, right? Which has basically a bunch of.
Like it's
Okay.
less expensive to run around the sparse. But if you have a dense model, that you could, of the same size that you could run, you would rather do that?
Yeah. Sorry. Well, this is really interesting, and we can get into it. But thanks for raising that. That's a great point.
This year developed your answer
to Cron. Sorry, yeah.
Yeah. So I guess what you're thinking is like you could think about like you have different AI models that are being trained. They're facing are doing very different experiments.
Mm-hmm.
But unlike humans, where they have to go to a conference, talk to each other, read the papers, we can do like this cross communication so much easier between like different groups of research, even if they have their same base model. Would that be your example that you had in mind?
Oh, no, I think that's a great point. That's not the example I had in mind. But it's totally true that, like, you might expect we would all just learn from each other's experiments very quickly. I mean, like, the different AI models would all learn from each other's experiments really quickly, and then they wouldn't learn as much from each other. So, like, lambda could still be low, but the like base is so high because they're all really capable that more than makes up for it. Again, I think the lambda thing is just the wrong way of modeling it. So I'll talk about that this afternoon, and that's why I'm a little hesitant to get into this. Because if you say lambda is lower but the base is higher, well, if you just scale up enough, that would imply that you're doing worse because you can share information with each other. That can't be right. Sorry, I know it's late as usual. But I'll just tell you about one paper which sort of digs into a way that the whole bigger brains thing could feed into a change in the parameters in the Jones model. Suppose that new ideas are made from binary combinations of existing idea. And that given a current stock of ideas big A, a researcher in a given period can like evaluate combinations drawn from some proportion of them. That's A to the phi. So this is, you'll see, this is a little bit of like a jerry-rigged model to get it to end up reducing to the Jones model. But anyway, I think it's kind of neat. So you can evaluate A to the phi ideas at once, some sample of the ideas. That means that there are 2 to the A to the phi combinations of ideas. And then if the rate at which you find a useful new combination increases logarithmically in the number of ideas you're considering, because, most, I don't know, maybe it's sublinear because most of these like random combinations will be like mustard ice cream or whatever. The rate at which you come up with new ideas ends up being proportional to like how many ideas you start out with raised to some power less than 1, just like the Jones model. Now that power will have to be between 0 and 1 rather than the negative number from beta equaling say 3. If here we're just talking about a single researcher, so we're not, parallelizability is outside the picture, but if lambda is 1, then beta's got to be 3, right? For lambda over beta to be a third, okay? But basically it reduces to the Jones model. And then you kind of recover the intuition that if an AI can consider a larger share of the existing stock of ideas at once, then ideas get harder to find more slowly for it, right? So there you go. Now let's break for 10 minutes and carry on. So we saw one reason why lambda might be higher in the AI case, better communication between the systems. A reason why beta might be lower, both of which would raise lambda over beta, beta being lower because of being able to evaluate more idea combos at once, so ideas get harder to find more slowly as the stock of ideas grows. Another consideration pointing in this direction, higher lambda over beta, is that as Eckert and Wu argue, the Bloom et al. Calculation is biased by the fact that as the pool of researchers has grown, average researcher ability has fallen. So it's like, yeah, the number of researchers has grown at 6% a year, but after weighting by ability, the number has not grown nearly as fast. Does that make sense? After correcting for this, they estimate that the sort of true lambda over beta is 3/5, which is still less than 1, which means you still won't get, you switch over to the super exponential regime just by automating R&D in the very long run, but it's closer. So in combination with the other factors, maybe we could get bumped over the edge. Yes?
Just curious if you know how heavy here the ability distribution is for this paper, because obviously it matters, right? Just how much better the last few people are.
It's a great point, and I don't know. Thanks. If anyone does know, yeah.
How do they infer ability this way?
Yeah, I think they look at, man, it's people coming out of college and I know one input is just the fact that like if you're proxying by degree, right, then like the premium to a particular degree, at least after you make some adjustments, has fallen or something. So it's based on a kind of general selection story, right? Yeah, I looked at this paper pretty carefully last fall, and now I'm not remembering it at all. Sorry. Well, but you can use it. I mean, yeah. Chat to it about this paper if you're interested. I'm just letting you know about it. And then finally, you can zoom into the hardware and software R&D processes in particular and estimate the sort of returns, the lambda over beta in those, and get very different numbers than you get for the economy as a whole. So Bloom et al. Do that same exercise, but looking at Moore's law. And, so famously, historically, semiconductor efficiency has like doubled every 18 months, and that's, something like a 70% annual growth rate. The number of people working to increase our semiconductor efficiency has been growing as well, but it's been growing like a fifth as fast, which implies a lambda over beta of 5 in compute if chip R&D has not benefited from spillovers from other industries. Does that make sense? So if they've been borrowing ideas that have been helping them out from all the growth and research from other industries, then lambda over beta is not necessarily so high, right? They might have been, even with a constant population of chip researchers, they could have sustained progress maybe with all the spillovers, which would have implied lambda over beta of infinity. Yeah, if something like this is right, then if R&D is automated and semiconductors are its only input, then growth will be explosive after all, right? Because you get the AL in the, yeah, whatever, you know how to do the calculation. S and Davidson have a report recently in which they look at the same question for software efficiency, meaning, to do a given task that like AI could do last year, you need less compute over time because we come up with more efficient algorithms. And the compute requirements of many AI capabilities have been roughly halving yearly. And so you can do your lambda over beta sort of steady state calculation and say, okay, the number of AI researchers is not doubling yearly. It's growing a little slower, which sort of implies lambda over beta greater than 1, even in software alone, at least before spillovers. And so if this is right, this means that the number of like effective virtual researchers could explode and then indirectly maybe drive explosive growth more generally, even absent any hardware improvements or even hardware increases, right? You just have a fixed computer that's able to simulate one researcher or whatever. At the end of the year, you have 2 virtual researchers working on the problem. And that more than outweighs the fact that, it's gotten harder to make further progress because of the bless you, because of the fact that ideas have gotten harder to find. So this would be like the pure software intelligence explosion scenario. Yeah, this is the evidence. You look at like how quickly we're lowering our compute requirements to do any given thing we could already do, right? And if that's like halving every year, right? If now we could train a model that's just as capable as GPT-2, but with, you know, 1/32 of the compute or whatever, however long GPT, whenever it came out, you can say, okay, how quickly have we been having to grow our population of AI researchers to make that happen? And it turns out we've been needing it to grow. The number of people working on improving our software efficiency has been less than doubling every year, they estimate, right? In which case, once one of the things you can do is algorithmic research on the chip, right? Then it would be able to sustain, like every time you double software efficiency, you do a full doubling of the number of virtual researchers you have on the computer. But you needed less than a doubling to sustain each doubling, historically. So you get a full doubling, which means that progress accelerates. So that's even without any hardware R&D improvements or anything. So this gives rise to like a range of scenarios, right? You could think that you know, even full automation of both production and R&D doesn't yield the, I'll for simplicity say hyperbolic growth. Obviously, it'll hit a ceiling eventually, but the crazy super exponential growth, even that wouldn't work out because of, say, hard natural resource constraints. So you could think that automating both production and R&D would yield it, but not automation of R&D alone because of the benchmark kind of point that lambda over beta seems to be less than 1 in R&D. Or you could think that automating R&D would yield hyperbolic growth, but only if we automate both the hardware and the software. Or you could believe in a software intelligence explosion, where even fixing the hardware, you get this like more, you know, what I was just saying about the software. It's like the recursive self-improvement scenario, sort of on the other end of the spectrum. And of course, you could do a more fine-grained decomposition, thinking about the different sources of chip efficiency, say, of which there are many, and you can check out some of them as explained by NVIDIA's chief scientist there, if you like. Digging into the software intelligence explosion scenario more. Yeah, we've got this like straightforward calculation that that like efficiency at doing something we could always do has been sort of doubling every year with less than doubling of the inputs. But of course, we've been making progress on other dimensions as well. We haven't just been lowering our compute requirements for doing what we could already do. We've been creating new capabilities and so on as well. And so maybe in some sense, software progress has been progressing even faster than at a rate of like doubling every year. I feel like it's worth remembering the other side of the coin, which is that maybe this is kind of all that matters. And the doubling of software efficiency is only interesting insofar as it's a proxy for increases in capabilities. Because if the only thing we had done over the past 5 years was like figure out a way to train 1 trillion copies of GPT-2, and that came with like no new capabilities, that would be completely worthless, even though numerically it would be like a huge software improvement. But anyway, so Tom Holden here and Tom Davidson try to get a bit more quantitative. They have a confidence interval. I don't know what this is, an 80% confidence interval? Sounds very confident. Anyway, they have a confidence interval of which contains 1 with like a central estimate of 1.2 in the software domain, which implies a software intelligence explosion, as I was just saying. But it's sort of a slow one because you're just a hair over the line. More explicitly, here's the model. So kind of outside the model, the thought is that technology in some economically relevant sense increases in AI performance. We're not modeling how. And that AI performance increases as we use more compute for training and inference and better algorithms, okay? So putting those together, we're interested in when this very precisely defined variable skyrockets because of how that'll filter through to the other stuff, but the other stuff is not inside the model. Got it? Okay. How is S precisely defined? Well, it's just in the standard like a factor augmenting sense. So you have like one benchmark, or you have a few narrow benchmarks, and you say, okay, with a certain amount of compute, we could hit those benchmarks in the past. We could we could perform that task in the past. We could train GPT-2, or we could train a model that could do at least as well as GPT-2 on this benchmark. And we say that S is double now what it was last year if we now need half as much compute to do that same thing. Okay? So S is like well defined. It might not be relevant to anything, but it's precise. We won't assume that S can be arbitrarily high for any given C. So it could be there's like only so much juice you can squeeze out of a given amount of compute. It might be that what that ceiling is rises the more compute you have, right? So when you double your compute, you could in principle more than double the amount of effective compute that it's possible to get out of that, because there could be some increasing returns to scale. But we're just going to be fixing C because we're thinking about the software-only intelligence explosion. So we don't need to take a stand on that. And we'll say that S is currently growing, as I was saying before, according to a Jones-style research function in its research effort. But we're in that edge Cobb-Douglas case, where our like composite research effort variable is a Cobb-Douglas combination of currently of human research effort and compute for experiments. So this isn't the compute done to like train the model and run the big training run. This is the compute to just like figure out, to do experiments, right? To figure out how a given training run would go and teach the researcher. Make sense? This is our production function for better software, better algorithm. And our question is going to be, what happens when software can take the place of the humans, the cognitive work? The software is still going to need to run experiments on the like dumb compute that just executes the experiments, but it can replace the humans. Once we can automate an AI researcher with some amount of compute, this is what our new production function is. So this is still the same, but now R is a composite of the compute used to like simulate the human researchers and the compute, not simulate, but like whatever, do whatever the human researchers were doing in this context. And the compute used for experiments. And the optimal Z that you'll want to pick is independent of the levels of S and C. You see that? Because you can just pull the Z1 minus Z thing out, Z to the alpha, 1 minus Z to the 1 minus alpha out. The Z that maximizes that coefficient doesn't depend on what comes after. So research inputs is just proportional to this Cobb-Douglas combination of software and compute. Okay? The proportion given by your optimal Z, the Z star. So plugging that in there, you see that GS is proportional to S. So S dot is proportional to S to the 1 minus beta plus alpha lambda. That's what S dot is proportional to, fixing compute. And then dividing through by S, you lose the 1. So GS is proportional to that thing. This is going to be positive if and only if R there is greater than 1. Okay? So they use R instead of the terms that we're using. But basically, R tells you how positive this is. And they're saying it's starting out at like, say like 0.2 or something. So you get a little bit of super exponential growth. To actually like try to estimate how fast and how big the software intelligence explosion would be if like today we suddenly figured out a way to like simulate the human researcher, You also need estimates of basically the coefficient here. So this is just proportional, right? But the proportion could be really low. So you need to know, there's different ways to pose the question in the same way to get at what this is. But basically it's like, if we suddenly move to this world, what would the coefficient be? One way to ask it, the way that they ask it, is how long would it take for S to double? So what would the initial doubling time be? That will get you the coefficient. You need to, I'll say number 3 first, actually. You need to know what alpha and lambda are, right? And you need to know, so given the doubling time, if you've got a coefficient and you've got alpha and lambda, you've also got alpha lambda minus beta. But they're going to assume that that actually doesn't stay constant, but that it declines as you approach that ceiling. Because as I was saying, they do impose a ceiling. So they say, okay, we're not going to assume like a literal singularity. We're going to say there's only so much juice you can squeeze out of that C fixed amount of compute that we have. So even though it starts out greater than 1, you don't get like that hyperbola that goes on forever. It bends down after a while. Yeah. So as I was saying, if you just restrict yourself to looking at, yeah, sorry, I glossed over this. But if you just restrict yourself to looking at S in the sense of, yeah, I didn't explain this well. Sorry, thank you. If you just restrict yourself to looking at S in the sense of being able to do the same thing more times with the same compute, then you would get a doubling time of like a year, historically. But they think that in the sense relevant to coming up with like virtual researchers that could get more done, this other stuff actually means that you should be using a faster doubling time. Yeah. Thank you. Sorry about that. So it's basically the researchers are getting smarter in addition to getting more numerous. Yeah. And again, I think that's maybe a little optimistic or something, or double counting, because it. But anyway, so let's say 3 months. It's kind of interesting because the results are, you got to fizzle pretty fast under these assumptions. So even if you think that they're being too optimistic, you end up concluding there isn't that much of an intelligence explosion. Cool. So right now, this sort of like augmented sense of software efficiency that's doubling every 3 months. What if we do our estimate of like, if we could suddenly unlock all this research ability because we're turning our compute into, we're turning all these NVIDIA chips or whatever into virtual researchers. How much more quickly would we go? Their estimate is we'd have like 30, from the outset, we'd have 30 virtual researchers per current actual researcher. And it could think 30 times as fast. So how much would that speed up the initial rate of progress? Naively, you might think like 900x. But it turns out these little sort of exponents that we're sticking on these variables make a big difference. And the median estimate ends up being 8x. And they assume a distribution that ranges from 2 to 32. Why is it so much less than 900? Because of that fact that software is not the only thing, human cognition or software like simulated human cognition is not the only input to R&D. They also need to run the experiments, and we're fixing the amount of compute they have to run experiments with. So it's the alpha. And then you've got that pure parallelizability constraint lambda. The pure parallelizability constraint doesn't knock down the fact that they can think 30 times as fast, right? If you just imagine like a movie of the Manhattan Project, then how fast they're building the first atomic bomb might be, it might not be as fast as if they got to work in sequence, right? The fact that they have to be in parallel might be slowing them down. But if you just make them all work 30 times as fast, you put it on 30x, I guess, video players don't usually allow for more than like 3x. Let's say you put it on 30x and they always like buzz around 30 times faster. You wouldn't have a parallelizability problem there, right? You get the full 30. But you'd still run into the lack of compute constraint. So if the alpha is 0.4, which is maybe something like the labor share in R&D for AI. We were looking at this before, how like in R&D as a whole, the labor share is like, 90% or whatever. But then in AI, it's much lower. So let's say that it's kind of conservative. Let's say the human labor share is only 40%. So currently, these labs are spending like 60% of their research budget on compute for experiments and 40% for researchers or whatever. Or, you know what I mean? Or they would if prices equaled marginal product. They've got your Cobb-Douglas research composition. The alpha is 0.4. And if lambda is 0.5, then the 30x that comes from having way more researchers is penalized by both. So you get the like 0.5 times 0.4 on that. That's a 0.2. And then the speed up, that gets the 0.4 because the lack of experiment compute. Make sense? So 900 ends up falling down to like 8. Then you've got that question of like, how far are we from that limit on how great the software can get? And you just have to make an assumption. Hard to have it be that well motivated, like what exact number you choose, but they make an assumption about how fast the exponent comes down for every doubling of s. And then finally you've got that estimate of the lambda alpha. So anyway, so those are the ingredients. You put it together. If we're currently doubling some sort of augmented notion of software quality every 3 months, and the initial speed up is 8x, then right when we unlock this ability, the first doubling in software quality happens not in 3 months, but in 3/8 of a month. Make sense? Yeah.
Going back to your functional forms, should I think about C as fixed?
That's the whole idea here. We're thinking about C as fixed because we're wondering what would happen if we fixed compute and like is the high returns to R&D in software alone enough to produce an intelligence explosion, right? Because that would be a really fast case. Because we wouldn't have to wait to like accumulate or redirect all these chips. And it's also maybe a kind of worrying case because like a single lab or government project or whatever could get to superintelligence soon after, or they're exploring the possibility that it could get to some really intense superintelligence very soon after we figure out a way to like simulate a human researcher, a human AI researcher.
And like visually, I could think of like S increasing, but as you increase, it's super concave because your C is still like holding like fixed, so you have like all these decreasing returns, right? For returns.
Yeah. So
the S is jumping super quickly.
Yeah. So with this Cobb-Douglas form, which you might disagree with, and which Parker will maybe disagree with this afternoon, but with this Cobb-Douglas form, the returns to better software decrease as the software gets better because they only have so much compute to work with, right? And that alpha in particular, well, you don't need to estimate it separately in some sense. But in my toy example here, alpha is like 0.4. Okay, so it's like it bends even steeper than like square root, right? But that could be the case, and yet you could still have the like hyperbola. Putting this aside, you could still have the hyperbola because like S is growing so fast, it's feeding on itself, and that outweighs it. Yeah, Hans.
Seems like a very speculative.
Yeah, well, I know a little bit about that, but maybe you can say more.
Yeah. Obviously, I mean, if you remember, like I was talking David's level of this guy's thing.
Mhm.
I don't know, you know this, like, he's got a bunch of dot points, I think.
It seems likely that. You know, it could be. Like only you only get like twice as much, or you get like, you know, 10 to the 100 items. So.
There are limited domains in which you can compare compute efficiency right now between like humans and machines in terms of like how much training you need to like learn how to drive a car or something, right? And with enough case studies like that, you can come up with an estimate of like, okay, if we were in that ballpark for the first generation of automated AI researchers, we would be like something like 4 orders of magnitude less efficient than humans, right? So that gives you a bound on how much room there would be for improvement in principle. Now, it could be that the hardware just doesn't allow for as efficient computation as the human brain, okay? But if it turns out the hardware is not a problem, then at least you get the 4 getting up to the human brain. The upper bound is the thing that's going to be much more speculative. And even this was obviously pretty speculative. Oh yeah, that's a great point. Maybe that's what he does. Yeah. Well, the thing you want to look at isn't just how much better they are than a human grandmaster, but some combination of how much better they are, and if you're just going to make them as good as a human grandmaster, how much more or less compute you need. Yeah, Zach, you know a bit about this.
Central points is like, it seems like the human brain is like, if it were to follow chinchilla scaling laws, has nowhere near enough data relative to parameters, and you could also imagine the data could be much more efficient. And they have like arguments for how much to quantify that, help get this range. I mean, there's other stuff in there too, but that's kind of the one that makes sense.
Cool. Yeah, that's great. Thanks for reminding us of that and bringing it up. Yeah, maybe you know about that. Yeah.
Yeah. Do you have any? So the Y variable is always just the S, right? And
yeah,
what are we mapping from S to
what matters?
Something we care about?
That's outside the scope of this paper. And it'll involve, I think, a pretty like kind of gears level thought about, you know, with really advanced AI, if we didn't have a lot of data, right, but it just kind of it got really sample efficient at using the data that's out there on the internet or whatever, to what extent would that speed up the production of like, you know, robots or something? And it's yeah, that would be it's rolling too much into this one model.
Practice is something like loss on training, and that's something like that.
No, so that would be a measure of like AI capabilities in some sense. Again, that also wouldn't be what we care about. But like the main component of this S is just literally like to get a fixed amount of loss.
Yes.
How much less compute do we need? Which is different from lowering, getting less loss. Yeah. Anyway, so they make these estimates, plug it into the model, and conclude that a software intelligence explosion will probably compress more than 6 years of AI software progress at current rates into 1 year. Again, if it happened now, if we suddenly started being able to fully automate the cognitive part of AI research, and would probably not compress more than 20 years into 1 year. This is talking about the first year, but that's also the fastest year, because we start out with that 8x speed up. The next speed up is even faster than the first, because we have that super exponential thing. We've got that R greater than 1. And the third doubling is faster still. But after the third, it starts slowing down again. Okay? So the first year, you end up with like an S, but you're already bending down by the end of the first year. R is their alpha lambda over beta. Okay? So interpreting R, you can read the thing and chew on what R kind of means conceptually. But the point is that R is greater than 1 and if and only if alpha lambda minus beta is greater than 0. So when R is greater than 1, you're in the super exponential regime. The higher S is, the faster it's growing. And when R is if R is falling, once R becomes less than 1, this is negative, and so the higher S is, the slower it's growing.
Because it almost feels like, what is endogenous here on this R to fall?
Oh,
Is there something in the model that is like, or it's just like an assumption that it will fall?
it's an assumption that there is some cap on how high S can be, at least for the compute that we have. Okay. So they have a range. It's like a Monte Carlo thing, but they have a range of possible upper limits. And obviously, if you have a constant R that's greater than 1, or even less than 1 actually, if you have a constant R, there's no bound on how good the tech can get. Right? So in order to put a bound, you need to like say, okay, R itself falls every time the software gets better. And they set it up so that it falls just fast enough that the ceiling is what the ceiling is expected to be.
So this is an assumption. So there's nothing on the model that's like endogenous. Like there's no function of R that reflects something, right? It's like,
well, no, there is. R starts out at like 1.2 as a central estimate, but it falls. So R is actually a function of S. Maybe I should have written this. But for each doubling of S, R falls at rate K. So this is how it starts out. But it's in the full model, it's a function of S. Sorry about that. No, yeah, great. So they think, yeah, like the quality of the algorithms will move a lot faster at first, but then it'll start slowing down. It'll compress on the business as usual path where you needed like humans to think up better experiments and run them and so on. At the current rate at which we're growing the number of researchers and the quantity of experimental compute, okay? And that's contributing to software progress. What this would mean, what this automation of the R&D would mean, is that even fixing the amount of compute, you would get 6 years of progress in a year, probably. Okay? Because we're assuming that we don't also simultaneously ramp up the amount of compute in that year. We get a huge increase of only one of the factors of production of better algorithms. Okay? Now, this is just a measure of how much faster we're making progress on the algorithms, but remember, like, the overall sort of amount of effective compute that we have is SC by definition, if S is like thought of as compute augmenting. And they estimate that currently, like the business as usual path, has S and C sort of growing at the same rate. So at the rate at which we've been increasing our effective compute, which is sort of a fuzzy variable given that we're not dealing with like purely the precise sense of S, but the sort of extended notion that rolls in capabilities and efficiency. But anyway, if S and C have been growing at about the same rate, but we're fixing C, then just that knocks down, like, you know, G like AI or whatever. G effective compute is going to be it's like 1/2 times GS plus 1/2 GC, and then no, it's not. It's going to be GS plus GC. Sorry, what's that?
Visually, you like for S, like big jump.
Sorry, I don't know what you mean. So I mean, it looks like that.
Yeah, but like the compression, like a line, like a vertical line.
It looks like a vertical line for a while, like for the first, you know,
Yeah,
half a year or something. Yeah. Anyway, so it ends up reducing to compressing 3 years of overall AI progress into 1 year. more likely than not, but probably not more than 10. So here's the distribution of outcomes in the Monte Carlo simulation that they use. Okay, so that's like an illustration of how using some alternative parameters can get you to a different conclusion than what you'd get to with the benchmark. Obviously, lots of other models you could make in this spirit. Yeah, Lily.
That like at its fastest, right?
That's right. That's in the first year. But remember, the first year is the fastest year. Yeah. All right. Now, briefly, I'll just run through the point that you can sort of think of all this in a task-based way, where R&D is a gross complements combination of tasks, and we're now automating R&D tasks. If we look at Alundu et al. Or whatever, and we say, LLMs are able to automate 20% of the tasks, and say, okay, what will that do to the speed of R&D progress? Obviously, it'll depend on how many of those tasks are R&D tasks. So I think the cleanest way to think about this is to say, at least in the Aghion et al. Story, where all increases in productivity are attributable to automation, right? People have been getting more productive precisely because they've been spread over ever fewer tasks. The most natural way to translate that to the R&D case is to say that now you have like more researchers, more effective researchers in R&D, and so you have like you see what I mean? Instead of having the tech contributing to tech progress 1 for 1, so it's A to the 1 minus beta, you say you have A to the lambda minus beta. Because the way that higher A helps out with speeding technological progress is just by unlocking more potential research. Okay, this is a change of variables, but let's make that change. And then you can see that for a wave of automation, that say like 20% or whatever that you get from the LLMs, for that to even temporarily speed subsequent R&D, it's got to automate the R&D tasks more than average. In fact, at least like 3 times more than average if lambda over beta is the third. So, because if you find out that we just made a big jump, like a big, every few years we make a jump, we automate more tasks, and the invention of LLMs was an unusually big jump. So now we're automating like 20% of tasks over the course of a few years. It's faster than usual. When you're asking, well, how much will that speed subsequent progress? On the one hand, this leap ahead means that ideas have gotten harder to find way faster, because we're now kind of off path, and you've got a steady state, and we're going to be pulled back toward the steady state. We made a big leap ahead, but the only way subsequent research will be even faster than it was before the leap is if the research tasks have been especially automated. So this A jumped up by a lot, but this, which is governing effective labor in production, only rose by a little. See what I mean? Automating R&D on its own speeds R&D. Automating stuff in general slows R&D because it's just easier to automate the easy tasks first and the hard tasks later. In fact, Acemoglu kind of gets into this when he makes this distinction between easy and hard tasks. He's like, oh, maybe says Acemoglu, estimates are actually overestimates because we're gonna automate the easy tasks first. And on balance, R&D is going to speed up, like even after the implementation of the automation that the technology in question allows for, if and only if the rate at which we've automated, the rate at which the advance in question automates the R&D tasks is at least beta over lambda times the rate at which it automates the tasks that are like indexing A in the first place. So here, like M's got to be at least, say, 3 times G. Got to automate R&D 3 times faster than production. And the Alundu et al. Estimate suggests that R&D tasks are more exposed than average. Zach said a bit about this, but not like 3 times more. So just fitting this to kind of a first pass fit to a task-based framework on some level would imply that we should think that R&D is like a lot harder now because we made such a big advance, right? And that outweighs the fact that these LLMs are helping a bit with R&D. Yeah, the capital share. Oh, there's never enough time. Okay, briefly, so the capital share and R, you can kind of maybe track the road to full automation in R&D by looking at the capital share within R&D. In the rho less than 0 case, the capital share will be a bad proxy because you've got the water and the dirt, and like maybe we're really near the finish line, but the capital share in R&D is still low, right? But you might think that the world's a bit more continuous than that. It's not like everything is a gross complement, and then suddenly you hop over to the AK world, and you're going to pass through a Cobb-Douglas scenario in the middle between the gross complementarity and the gross substitution. And so you can look at the how high in the Cobb-Douglas edge case, how high does the capital share in R&D have to be for us to switch into the hyperbolic regime? Obviously, for this to be possible, it's got to be that. This is like applying the Zera task model to automation, right? The Zera is the Cobb-Douglas task model. I mean, sorry, to the automation of R&D. See what we're doing here? We're imagining that R&D is a Zera-style composition of tasks. And so if you're going to be using a kind of model like that at the back of your head to learn something from the capital share in R&D, you'll find that it doesn't look like we're approaching full automation in R&D even so. So the BEA data, Zach put this together, sorry, but just briefly, the data from the BEA shows no trend in the labor share for R&D as a whole. It's always been very high at like 90%. And some NSF data, university R&D in particular, shows, if anything, a higher and rising labor share of R&D. There's a paper that looks at the capital share in AI R&D, particularly in computer vision, and finds that it's much higher. They have a whole methodology, which is very interesting, and you can look into if you like. But that's the paper that this picture actually comes from. They find basically every kind of AI R&D has a higher capital share than like every other kind of R&D. And it would be nice to know whether it was rising over time. Unfortunately, labs don't tell you how much they're spending on experimental compute versus researchers, but there's some tenuous evidence that the capital share in AI R&D is even higher than in the domains that Besseroglu et al. Look at, and also some limited evidence that it might be rising. Even if it isn't rising, though, if R&D sort of shifts from other sectors to AI, then that would yield an increase in the aggregate capital share in R&D, which would imply an ultimate increase to the growth rate, at least in a sort of stylized Cobb-Douglas model of how it all composes.